somehow. And you're still encouraged, despite whatever happened last lecture, you want to know how we're going to end this story, right? So what did we learn from last lecture? Right, so if we do a gravitational path integral in the way that we think was a reasonable way how to do a gravitational path integral for pure AdS₃ gravity, we didn't get a trace-like interpretation. So we might be very discouraged because it looks like quantum gravity is even harder than, than expected. So I am very happy that you're not discouraged. That's the right attitude. Yes. No, bring it on. No. Okay, great. No, that's it. Yeah, I was a little bit, to be honest, when that paper came out, the Maloney-Witten paper came out, I was a little bit saddened because, I don't know, it would have been nice if it worked out, right? I agree. But okay, but like the thing is that that computation is presenting for us a challenge. It's presenting to us many questions, many reasons why this is still an active research field and there's many things to explore. And so I wanted in this last lecture to cover the third topic, in which I'm going to now try to have a different approach on how to think about quantum gravity in AdS₃. And basically, finally, today, we're going to make use of the correspondence. So what I want to do is basically define quantum gravity via the conformal field theory, okay? So what am I intending here? So basically, conformal field theory as a definition of AdS quantum gravity, okay? Now, this is just an approach that I'm going to take, okay? This, you might object to this, you might think, you might have many opinions, but this is how I'm going to move forward, okay? If you have a different way how to do it, then get invited to give lectures and do it that way. Okay, now, with this attitude, if the conformal field theory defines for me AdS quantum gravity, it poses, it's still not something like, okay, you can write that as an equation, but I still haven't learned anything. And I want to learn, I want to learn from like the things that were challenging from the gravitational side. I want to actually understand what's going on. And as written here on the blackboard, if I just leave it at that and be like, okay, kids, we're done. This is it. This is, you can just go home and watch TV. It's not great. And so what we want to do more precisely, so this gives rise, in some sense, to several, these are all basically the same questions. It's the same question, but phrased kind of differently, just to give you an idea of what's going on. But basically, what I want to address is how does gravity basically emerge from the CFT? So if you do not believe, or if you're not convinced by AdS CFT, or well, just even if you're convinced about it, basically, yeah. So how does gravity emerge from the CFT? Perhaps a more practical point of view is how do you organize observables in the CFT such that geometry, or if you want gravity, is manifest. And finally, there's also a very important aspect of this, is what are the conditions so there's a sense in which any conformal field theory, if it depends on how you take the correspondence, but I don't know, from my point of view, there's a sense in which the correspondence is telling me that any conformal field theory should have a dual equivalent of something that we will call quantum gravity. But we're also interested not just on like a formal definition of quantum gravity. We want to know what are the conditions such that this AdS, so what are the conditions, sorry, let me write it as, what are the conditions on the CFT such that classical gravity emerges? Because classical gravity is something that we understand. And so the duality can just spell out to us very, very quantum theories of gravity. But in order for us to feel comfortable and say, yes, we understand what's going on, we want to also know when we will have access to a classical regime and then really touch with the classical intuition that we have of gravity in terms of general relativity. Okay? Now, I am not going to give you answers to each of these questions. These are open questions. So these are things for you to think about on like where the field is going. But what I want to do in this lecture is to illustrate what does it mean to answer them. Okay, I'll give you a small glimpse of whatever I can cover in this next hour of like how does it look like answering these questions. Okay, how do you have to think about this? And so the first thing that we're going to do in that context is look at universal aspects of conformal field theories in 2 dimensions. Okay? So there's many things here that we can say that is particularly that we can do regarding answering these questions without actually saying anything about a specific conformal field theory. So the things that I want to do are going to be basically applicable for any theory. So my only assumptions in what I'm going to say in the following is that I want the CFT to be unitary and compact. Compact here means that the energy spectrum is discrete. You can have CFTs with continuous spectrum in some portions, and I don't want that. So, for instance, I'm removing from this discussion Liouville. There was a nice talk on Monday about Liouville. This is not within my, it's a great theory, by the way, but not going to be part of the discussion. I'm also going to assume that the central charge of the CFT is bigger than 1. This is not necessary, but we will see why we do it in a bit. If you consider conformal field theories with central charge less than 1, there's going to be, I will have to start putting some caveats here and there, and I just don't want to do it because I don't have the time. And then you'll see also why, if I wanted to answer this last question, this is a perfectly fine answer. And lastly, I'm also going to assume that the only current is the stress tensor. again, this you can weaken. You can, for instance, we can generalize this for things that are supersymmetric. You can also have R symmetries and things like that. But in terms of like how am I going to write the equations, how I'm going to present the derivations, the only thing that I need is basically the existence of the stress tensor as a current, which is a very mild, well, it's not an assumption. It's a perfectly fine thing to do, but like if you do have other currents, again, you do have to be a little bit careful with some of the computations. Again, they're completely tractable and you can see what's going on, but I just don't want to write very cumbersome equations that include like the absolutely more general cases, okay? Now, one thing that I'm not going to do, if you're not familiar with conformal field theories in 2 dimensions, I'm really sorry, you will just have to let it go, because I don't have time to give a mini course on conformal field theories in 2 dimensions. So I hope if there are things that are not clear, that you don't follow, maybe ask me after, or unless it's very, very urgent for the clarity of the lecture, do ask me. But I am going to assume that there's a basic knowledge on conformal field theories in 2 dimensions. Is that roughly okay with everyone-ish? You don't really have an option, because even if you tell me it's not okay, I'm still not going to give an introduction to conformal field theory and also try to address all of these questions. But again, like like you can ask me for like reviews, the Big Yellow Book. There's tons of references, at very different levels, where you can see more about like the things that I'm doing. Okay. Okay. Very good. So let's first talk about these universal things. Okay, where these are basically the assumptions that I'm putting on my conformal field theory. Okay. So the first thing that I want to highlight as universal, so first let's look at the partition function of a CFT. And I'm going to focus on the partition function just because during the gravity lectures, we were talking a lot about the path integral, the partition functions, black hole entropy. So it's kind of like the natural thing to go and look at, okay? And so what happens in the context of the partition function? So what we're going to do, so CFTs, a 2-dimensional CFT, basically, so I'm going to be, the setup that I have in mind is that you have a conformal field theory living on a cylinder. So we're here, there's some angle, and there's some time. And we're going to go to Euclidean signature very familiarly, so we're going to put this on a torus. Again, this is not the solid torus of the Euclidean BT set. This is like a torus, like a 2-dimensional surface, just to not make things confusing. So here there will be phi and time, roughly speaking. And so I'm going to define Euclidean time. So as we place the theory on a torus, it's useful to introduce this complex variable again. So very similar to what we were doing in higher dimensions. I just want to make sure that this torus will be defined by those identifications, where I'm going to write tau as 1/2 pi of theta plus I beta. Okay, so we're putting the theory on that torus, and when you put the theory on that torus, the natural thing to compute is then the partition function, which is defined. So then as a function of tau and tau bar, which you can write like this. It's trace of e to the minus beta h plus I theta j. So beta and theta are those 2 parameters there. In more CFT notation, it's common to rewrite this in this more fancy notation, which is very similar notation to what we were using in the previous lecture. And the relationship between the Hamiltonian and those L0. So here, I have to define a few things. So J is the difference. Like this. So L0 and L0 bar are the zero modes of the Virasoro times Virasoro for each copy of the CFT. And each Virasoro has central extension. In this case, maybe I should also put another assumption here. I'm taking central charge equal to 1, and I'm taking that the left and the right moving central charge is equal to each other, and that's what I'm calling C. Okay? You can again generalize this discussion when systems have different central charges, but again, I don't want to have too much notation. Okay? So these are the zero modes defined on the plane. And H and J are basically the zero modes. The reason why you get this minus C over 24 is because these are the ones defined on the cylinder. Okay? So the minus C over 24 is the Casimir energy that you get between mapping the charges from the plane to the cylinder. Okay. Now, you can say more about this. So if you are in a 2D CFT, there's two more things that you can say about this. So this partition function, of course, yeah, it's counting over all of the states, but a convenient way how to cast it is to be a bit more explicit. So in conformal field theories, states have very nice way how to organize them. You basically just have two types of states, of local states, I should say. You have what's called a primary state, and then you have descendants of the primary states. So what's very convenient in 2D CFTs is to write down this partition function as basically a contribution. I'll explain the notation in a second. So you decompose it. You decompose it as a function of what's called characters. So in this sum, in this way of writing it, I'm singling a contribution that comes from the vacuum state. And then I have a sum over all primaries. And these functions chi, basically, so the characters chi, so sorry, let me see. Yeah. So here, chi h, it's yeah, it's defined, so chi of tau it's defined like this, where eta is again the eta Dedekind function. So just to remind you, this eta was q over 1 over 24 times the product of L equal to 1 up to infinity of 1 minus q to the L. And this object here counts the descendants of the primary state, okay? So this thing counts the descendants of the primary H. Same definition, sorry, here there's an H bar, so same definition for H bar. And then the vacuum one, so the vacuum state is also, in a sense, a primary, but it has additional null states. So it's just so it's roughly the same function. You put H equal to 0 because that's the vacuum state. It also will have the eta function, but this part over here is the thing that is removing one of the null states. So this counts descendants of the vacuum, where null states are removed. So that's why the counting is slightly different from the generic primary, okay? But this is like, again, if you open the big yellow book and you ask, and you see in the chapter where they compute partition functions of CFTs, you'll see this formulas, okay? So this is the traditional way how you write down a CFT partition function. And just to go back a little bit to the initial question there, if you look at this formula, nothing here yells at you, like screams to you, gravity. So that's why even when you say, the CFT clearly defines gravity, like you look at this, it's like, okay, sure. So let's try to kind of slowly understand how would gravity kind of emerge out of this picture. How would you see gravity showing up? Okay. Now, when you study this partition function, so the second property, so here I told you how we organize it. So this is a very nice organization of the partition function in terms of primaries and descendants. So and descendant states. But then there's another very useful property of this partition function, and is the fact that on the torus, so here we characterize the periodicities with this in this fashion, but actually the conformal transformations, the conformal symmetry of the theory tells you that you can do any SL2 set transformation here on these coordinates, and it will be the equivalent torus, okay? So the outcome is that the conformal invariance in 2D basically implies what's called modular invariance, which are SL2 set transformations on the torus. And from the point of view of the partition function, this means that the partition function of tau and tau bar is equal to the partition function evaluated at A tau plus B over C tau plus D with the A, B, C, and D belonging to SL2 set, okay? And this is quite a very, very powerful symmetry in conformal field theories. It's actually one of the ways how you can, when the central charge is less than 1, so actually the regime that we're not going to study, but for low values of the central charge, this type of symmetry actually fixes almost the theories. So you can basically like bootstrap conformal field theories, just not, you still need to do a little bit more. It's not enough, but it does get you very close at determining what are all physical theories when the central charge is less than 1. So it's a very powerful symmetry. And very special to 2D, of course. Okay, so with that, what we're going to do now is see that regardless the CFT that I have, so yeah, these are nice questions. I think I'm not going to erase those questions. We're going to erase this. So what I want to do is, in regards of this universal behavior, is basically extract, so with this, We can already extract universal properties. So what I'm going to do, there's many, I'll list to you many properties that you can do, many observables that you can constrain with just those symmetries, but the one that I will focus on, it's what's called the Cardy formula. Okay, so the key is basically to use modular invariance. And actually, I don't have to, the modular invariance is quite rich. There's a whole family, like there's an infinite set of A, B, C's, and D's that you can pick. But I actually have to just look at one of those transformations. So for choices of A, B, C, and D, you can very easily see that modular invariance in particular implies that set of tau and tau bar should be the same as set at tau and minus 1 over tau. So I'm going to do a simplification. And actually, I was going to give you this as a problem to generalize it to more general cases. I'm going to turn off theta, just because the equations are a little bit simpler. And this means that tau will just be a purely imaginary number. So it will be I times beta over 2 pi. And so then the consequence, this equation, so then you would just write down the partition function as a function of beta. And what this equation is telling you is that the partition function as a function of beta is equal to the partition function as a function of 4 pi over beta. Okay? So what does that equation tell us? That equation, for instance, is telling us that if I take beta to be very small, so what is small beta? It's high temperature. So if I evaluate the partition function, let's say, at high values of the temperature, it's the same as evaluating the partition function at low temperatures. So here, beta prime, which is 1 over 4 pi squared over beta, is going to infinity, which is low temperatures. So something very special about 2D CFTs is that there's always a relationship. There's a tie between what's happening at low temperatures with what's happening at high temperatures, okay? As a consequence of modular invariance. So let's use this. And the way that we're going to use this is that basically at low temperatures, we know from these expressions that, and also from my assumptions, that the spectrum is basically organized in terms of like the various states that I have. And I have a lowest energy state, which is the vacuum. And then I have excited states. So just by vacuum here, just also to be clear, so this is the state that has H and H bar equal to 0. And then I have a sum over the states that have bigger values of H. And so at low temperatures, the most dominant contribution should just be the vacuum state, right? So tau bar is complex conjugate of tau. So tau is a complex number, which I decomposed into 2 real parameters, theta and beta. So just recall that tau is Okay. So then at low temperatures, so from this point of view, so if I focus now on this part of the equation, if you're taking a low temperature limit, the dominant contribution, which is not to anyone's surprise, should be, I'm going to write down here the vacuum energy, just to be clear that it's like the vacuum value that I have from here, okay? And then there will be corrections, so I'll pull off like a power of E vacuum, and then if you see what will come out next, this is just organized as a sum over states. There will be the first excited state, which it can either be a primary or it can be a descendant, depending on the spectrum. I don't care. But basically, anything that is excited will have this difference will be positive. And so if beta is going to 0, this is going to be highly suppressed, right? So the most important contribution is going to be the vacuum contribution. Okay? And just to be clear in terms of the notation that I'm putting there, E vacuum, if you read it off from the previous equations, is minus C over 12. Okay? That's the Casimir energy associated to the vacuum state. Okay? So what do we get out of this? So we get that basically set of beta, so at high temperatures, I can approximate my partition function by e to the minus 4 pi squared over beta times the energy of the vacuum. Okay? And now we can do thermodynamics. So for instance, the entropy of the system would be 1 minus beta d beta log C. So that's just the usual, the thermodynamic expression for the entropy. I know what Z is. So then you just take a derivative, and this is going to give you 2 pi squared over 3 times C 1 over beta. I'll write it as a function of the temperature, just the inverse. So it's 2 pi squared over C times T. Okay? So the entropy, so this is known as the Cardy formula. And it's basically saying that the number of states at high temperatures is universal. I don't care which primaries you have. I don't care like what are the details of the CFT. Every CFT₂ is going to have at high temperatures an entropy that goes linear with the temperature, and the only thing that you need to know about the theory is what its value of the central charge. Now, what was the key assumption? And that's also why I listed assumptions here. So for instance, in this step, I used the fact that the theories are unitary and compact. If the system is not unitary, then energies are not bounded by below necessarily, or the vacuum state at least is not the lowest one. And compact is basically that I have discrete values of energy, so there's a meaningful gap between the vacuum and the next excited state. So you need to have those two features for this to hold. So this is where my assumptions were coming. The first assumption that I wrote was coming in here, okay? So yeah. You are assuming that the Hamiltonian is bounded from below and that there's a gap between the vacuum state and the first excited state in the system. Provided those two assumptions, this is always true for any CFT₂. Yes? Of the CFT. It's counting for you the collection of, it's telling you about the ensemble of primaries and descendants. And they're also states. because there's an operator state mapping. Yes, yeah. So look, I know we like to, in field theory, we like to talk about operators, but field theories also have states. So yeah, so then I'm just counting the state. This is basically, this is the number of states. The entropy will count the number of states, which in this case is mostly going to be dominated by primaries plus descendants at high temperatures. Yeah, I think there was another question up there. Yes, it will also, you do have to be, yes, it will also work for C less than 1. Because I haven't, the only thing that you have to be, the corrections, like there's other things that you have to be careful about. Exactly, so, but again, like, yeah, these expressions, so that's also, so in these expressions I used that C was bigger than 1. But the fact that there's a lowest, like the only thing that I'm doing here, if you want, is just projecting to the lowest energy state. That's all I did. And theories with C less than 1 also have like a lowest energy state. So there's nothing funny from that point of view. Yeah. But like, because I'm not really, I didn't have to use the explicit expression for the descendants. This is just to basically illustrate that the descendants are controlled by symmetries, and the input of the theory, like the thing that you don't know about the CFT a priori is like, what is the spectrum of primaries? Yeah. Was there another question? Yes. Why can it be 1? It's in this expression. So these type of expressions are valid. They assume that C is bigger than 1. It's related to the question he was asking me. But so the number, if the central charge is less than 1, equal to 1? Yeah, you can also put it equal to 1. That's also fine. There's nothing wrong with the, like, yeah, you will just put here a 1. So a free boson, we'll just have this with 1. There's nothing wrong, like, the thing, okay, again, you can, like, many of these things, that's why I said, like, the only thing that I used here was unitarity and compactness. I didn't tell you that I used that C was bigger than 1. Like, yeah, so there are certain, there's some of the equations that I'm writing that assume that C is bigger than 1. C equal to 1, it's a limit. You have to be careful because it's also like a limit of the minimum. I just don't want to, like, yeah, okay. This? No, here I'm taking an approximation. So I'm just saying, like, this is a true statement. And then, so this is true for any temperature that I want. It's an exact statement of the CFT that this is invariant. And then, that's why I said here, then at high temperatures, so when beta is going to 0, in the limit, so of course there's corrections here, but the leading contribution at high temperatures is just this one. That's all that this is saying. So I'm taking the limit of a function. That's. Why would I? Because I don't know what the answer is. Well, like in a sense, I'm trying to infer it, like, so use what you know. So which part of the expression do you have control over? I have control on this side, so let's use this side. Like, this is the part that I'm trying to understand, and so I'm going to try to understand it by mapping it to something that I already know. And the thing that I know, because it's part of my assumptions, is that the theory had a vacuum state, because it was a unitary and compact CFT. Yes, yes. Exactly. Yeah, so that's all that's happening. So this is true, and then I'm just saying, okay, it's true, but then this function has an expansion in beta, and then I'm expanding it in beta. That's all I'm doing. Yeah. Because it's also about where the function is convergent in terms of its expansion. So it's easier to see the convergence of the function when you're at low temperatures. Like beta prime going to infinity is where the partition functions tend to be convergent. And so then you expand it around those convergent points. Yeah. But then I'm inferring something about it in a different point in the complex plane, if you wish. But yeah, but always in physics, like you have to make mileage of the things that you already know to learn new things. And like, so always exploit the thing that you already know. And that's what makes this formula beautiful, because I knew the vacuum, and then it gave me for free the high energy stuff. So now I'm telling you, from knowing that the theory had a vacuum, now I know that there's a lot of heavy configurations here, okay? Now, the energy, so let's continue here. So I can also compute the energy. The energy is a derivative with respect to beta of set. Of 1 over beta squared. And so basically we have this, there's different, so let me write this. Like this. And so there's different also ways. It's also useful to write down this Cardy formula as a function. So you can, of course, write it as a function of the temperature, or you can write it as a function of the energy. So it goes linearly with the temperature. It goes like a square root of the energy. But this is basically the very famous Cardy formula for the entropy of states. Okay? Now, if you wanted to add, so I turn off the angular velocity. So if we add, so you can do as homework. So keep theta different from 0. And then the generalization of what you're going to get you can see that you will get 2 contributions. And so you will get 2 square roots, okay, instead of just 1. So, sorry, L0 bar. So that's a generalization if now you have both energy and angular momentum. So remember, energy is the sum, angular momentum is the difference, but it's more convenient to write it in terms of these L0s and L0 bars, okay? So that's a generalization of the Cardy formula. Good. So now with that, let's see if gravity starts showing up. So you might get anxious and ask yourself, well, I already notice black holes at this stage. So let's recall from BT set that the entropy of the black hole was given by pi times r plus over 2g. Right? That was the Bekenstein-Hawking entropy. Now, let's rewrite this. So this r plus, so we had these definitions that r plus plus r minus was this, and our plus times our minus. Sorry, there's factors of L here that I'm forgetting because I was keeping all the L's. And then our plus times our minus was 4GJ times L. Okay? So you can basically solve from these two equations what R plus is. So let me write this down. Instead of as a function of R plus, I want to write it as a function of mass and angular momentum. So with some algebra, you can convince yourself that that's true. And if then you use that C is equal to 3L over 2G. So instead of using G Newton, trade it for the central charge. And that the map between these two things is this. You want to guess what you will get as a function. This is the same expression. So let me call that S Cardy. It matches. Exactly the same answer. Was there a question? No? No? Okay. Yay. Okay. So this was noticed around, I think, yeah, it was 97 by Andrew Strominger. It's a version of the Strominger-Vafa computation that explains the entropy of black holes in string theory. But it looks like CFTs knows about black holes. A little bit. Cool, no? And even with the coefficients, there's not even like, oh, it's kind of like it has the right units, or it's like, no, it's like the thing matches like perfectly. This area was secretly the entropy of black holes. And so now you might say, great, any CFT can capture black hole physics. Right? Right? Any objections to that statement? Where did the central charge have to be bigger than 1? Oh, but again, for the derivation of Cardy, the only thing I used was unitarity and compactness. Okay. I don't know, how do we feel like? Who was asking that? There, excellent question. So let's inspect this a little bit more, because it is quite remarkable that you get the same dependence. But this is what I would call a necessary condition of AdS₃. If AdS₃ was false, then we would have a problem. But what I want to test, and the reason why I'm being kind of like evil like this, the question is this sufficient? Why? With so much confidence.
You matched a single number. There are a lot of numbers.
There's a lot of Fine, there's a lot of numbers that we need to match. But even within the context of this computation, you have to be careful. Okay? Just to illustrate, because a lot of people, once they get in, and it's something that you do have to be careful with papers, like they will tell you like, this thing matched, therefore this is going on. Like, and there's big statements made. Again, like it is true, it's quite remarkable. This is beautiful. This is like absolutely amazing. It's one of like the biggest, like it's an amazing success of holography. And I don't want to like diminish this at all. But given that we really, really want to understand what quantum gravity is and what black hole microstates are, I need to go into more detail, okay? I want more than this. I really want to understand what's going on. But this already like is quite a lot, okay? So what I'm going to say next, don't take it as like as a criticism, but take it more as like a challenge that we want more, okay? So we really want to have a fine-grained understanding of it. So because I want sharp answers to those questions. That's my objective in life. And so let's inspect of the matching. Okay, so from the perspective of the CFT, of the CFT₂, when you are deriving this S Cardy, as it was very clear from the derivations, I was doing an expansion in temperature, right? So I was doing this is a result that is valid for high temperatures. So the temperature here, let me write it. So of course, this is valid. When the temperature is high, you can also make a statement because we know how energy is related to temperature. This will also tell you basically that the energy of the solution, so if you write the T squared, there's more rigorous ways how to do this, but just based on like how we've been deriving things, you would have said E over C has to be much bigger than 1. And so another way how to state this is that, for instance, if C is fixed, this just tells you that this will be valid when energies are very big. If C is large, is going to infinity, then it tells you that there's a hierarchy. Basically, the energy has to be much bigger than the central charge, okay? Such that the temperature of the system is high. So this is the validity, this is the regime of validity of the Cardy formula, okay? This equation here, these statements here are telling me what type of primaries, what type of states are you counting when you say that the entropy of the system went like a square root of the energy, okay? It's giving you a characterization of like the type of states that you're counting. Now, from the point of view of gravity, no, I'm just trying to, like what I'm doing here, I'm just trying to understand what are the states, like, so you have an energy spectrum, right? And I'm saying, when is this entropy a good approximation for that density of states? And what this is telling me is like, that entropy is going to be a good approximation for the density of states when the energies are above C. So imagine like you have some density of states, right? And let's say, so here you will have like the vacuum state minus C over 12, and then you will have other configurations, then you will have some state with 0 energy. And so what I'm saying is that Cardy does a good description when the energies basically here are much bigger than the value of the central charge. Here, it's a good approximation to say that D of E goes like e to the square root of C times E with the prefactors. Let's see it. Let's see what is the regime of validity of the Bekenstein-Hawking entropy. Let's do that, right? So from this point of view, I have yeah, but then I'm expanding at high temperatures. So this, again, only at high temperatures, the partition function is well approximated by this. So then only at high temperatures, the entropy is given by this formula, because I'm using in here this expression. No, it's just describing the states at high temperature. Yeah. Yeah. If you want the states at any given temperature, then you compute the partition function and you extract the appropriate Fourier coefficient. But yeah, so here I'm only doing, so this maybe at high temperatures. So this is the thermodynamics at high temperature. Like, yeah. Of course, there's other, like for instance, you wanted to know what a coefficient was at any given temperature. These are modular forms. There's very fancy mathematics associated with the Hardy-Ramanujan formula, or you have Rademacher expansion. So there's all sorts of like fancy mathematics. And then the expression for the density of states is like some very complicated thing. But like the only thing I'm illustrating here is that if you take the temperature high, there's a universal behavior of those coefficients. So when I'm very high up in the spectrum, then the density of states always goes like an exponential square root of E, which was the original statement of Hardy and Ramanujan, that basically the number of partitions, they didn't do it for CFTs, they did it for specific modular forms. They were in particular looking at the AdS₃ function, and they said, then the number of partitions that the AdS₃ function counts grows like the square root of n. So they're asymptotic formulas. So this is an asymptotic expansion for the number of states that the system has. Yeah, and by asymptotic, like in the mathematics, asymptotics means large values of the parameters, which in physics, the large parameter is the energy. Did you take notes? Did you take notes? Okay, so what was the Hawking temperature? Okay, look at your notes and then answer your question. Okay. Okay. Very good. Okay, so the entropy of the black hole, as we have written there, it's R plus over G Newton, right? And we did this computation in a semi-classical theory, in a semi-classical approximation. So you can trust the Bekenstein-Hawking entropy when basically the size of the black hole is much bigger than the Planck length of the system, right? So this is what tells you that you can trust semi-classical physics. Okay, so I will trust just looking at the tree-level action, I would trust just doing these semi-classical computations if R plus is much bigger than G, so that anything quantum kind of gets suppressed, right? We all agree with that statement? Yeah, and the formula is quite simple. There's nothing else there. Okay, so let's translate. So this is written in gravitational variables, R plus, a size of a horizon, G. So let's translate it to the language of the CFT. So what would it mean, given that I have all these relationships, so given that I have all these ways how things are related, how would I translate this to the CFT? And so you start by doing something very insightful. You square that. Why am I squaring that? Because, okay, again, I'm going to do it when I don't have rotation, so R minus is 0. So you can see from here that R plus squared is basically the mass of the black hole, okay? And so then if you translate this, this is going to be, and you rearrange things, the statement is equivalent to the statement that M times L again is much bigger than G. I'm going to put this L down here. And this ratio, G over L, is what controls the central charge, right? So this is telling me that E times C has to be much bigger than 1. And it is also telling me, because part of the semi-classical effect, so also coming as a consequence of what it means to be semi-classical in gravity, semi-classical in gravity means that L, the AdS radius, is much bigger than G, because this is the coupling that enters in the action, in the Einstein-Hilbert action. So I also have that C has to be much bigger than 1. So that's also one reason why I was not bothering too much with like, oh, if C is equal to 1 or less than 1. It's like, yeah. Like, of course, you can do holography for finite values of C. There's no problem, but because we're doing this black hole physics, we have this. Okay? And so all of you are very smart people, and it's kind of obvious that these conditions are not the same as those conditions. They're compatible, but they're not the same. Right? So there's a mismatch in the regime of validity of when do you trust this versus when do you trust this. Okay? So from the perspective also of the free energy, of F, recall that when we drew the free energy of the black hole, of 3D gravity, we had this beautiful plot here, where here we had minus C over 12, and here we had like the free energy that went like, so here it didn't have beta dependence, and here it went like, sorry, I'm blanking on the formulas, and let me not, one of you will correct me. Yeah, 1 over beta squared. And so this is telling me, and remember, this was the contribution from thermal AdS. This was the contribution from BTZ. And what this plot was telling me here was that the entropy, so the dominance of the BTZ black hole, the thing that dominated the ensemble from the gravitational perspective, was the black hole up to temperatures of basically of 1 over 2 pi. That's not high temperature. So the gravitational system has a huge amount of entropy up to that temperature, which is the equivalent statement that in order for you to be basically trusting of the Bekenstein-Hawking entropy, you don't need the energy to be necessarily large. You just need E times C to be large, but C is already big. So you can lower the energy and still be okay. You guys see what I mean? No. Okay? So in gravity, black holes dominate the ensemble, or if you want, the density of states. Up to low temperatures. Cardy is only valid at high temperatures. So in a sense, what the CFT, what we have discovered from the CFT is basically when you're at high temperatures, we just made a match with this function like this. This is what we're matching. So what happened in that board, and that's why I wrote it as a necessary condition, like this is what you generically get from Cardy, and it's like it matches beautifully, same coefficients, absolutely no problem. But then the CFT will tell me, like, look, if you start lowering the temperature, we'll need more details. And this is where Holography 2.0, we graduate from 1997, and we ask ourselves the question, when can I actually reproduce this? What are the CFTs? So now my question gets a bit sharper in trying to understand the emergence of the CFT answers. So then you can ask the question of like, which CFTs have the same phase diagram? By phase diagram, this is what I mean. So plotting the free energy as a function of temperature. As AdS₃ gravity. Okay? So now we can see, like, in regards to my last question, it's like, okay, so I really wanted to see this classical picture emerge. That's what this phase diagram is. I wanted to see this classical picture emerge. If I just say nothing about the CFT, besides the fact that it was compact and unitary, I'm only getting here, and well, and of course the CFT, I should also say, because of modular invariance, the CFT gives me like this bit, and it gives me that bit, so that's what I did with modular invariance. So I was able to say, at low temperatures, the vacuum dominates, at high temperatures, the Cardy dominates. But then I want to, if I really wanted to match this specific curve, is like, what classes of CFTs will do that? Okay? Something that you can convince yourself very quickly is that your favorite free boson will not do the trick. So the typical like CFT₂ will not have that phase diagram. And so then you have to think a bit more. And there's actually a beautiful paper that answered this question. So the answer is in a paper by Hartman, Keller, and Stoica, it goes under the name of HKS. And they basically put, they gave criteria on like what classes of CFTs, they gave a condition, they gave a necessary condition for this, such that the CFT would have this phase diagram, okay? And so the answer is that a CFT will have, and it's written in terms, so this phase diagram is basically the phase diagram for a Hawking-Page transition. If two things happen. So the first thing that needs to happen, it's of course that the central charge of the CFT, so you're always looking at CFTs that need to have large values of central charges. So phase transitions are not going to happen at any finite value of C, okay? So it's an effect, the phase transition comes about because you took a large C limit. This is also the large N limit in the jargon of AdS CFT. This is needed, and they basically also put a condition that the density of states had to be less than or equal, actually, either, well, let me, less than the exponential of the energy for energies that are big, but basically do not scale with a central charge. So from the point of view of the phase from the point of view of the density of states, what they're saying is that, roughly speaking, you have the vacuum state, and then you will have states, so the states that will be of the black hole type, so states which will have E times C much bigger than 1, so this will be like black hole type states. These guys will have a growth. What they showed is that, sorry, I'm going around in circles. So you will have basically vacuum states, and then at some point you will have states that we will call like heavy, and will map to black holes. What they did is basically put a restriction on the states that are in between here. So they're putting a restriction on states that are, roughly speaking, lying in this regime, where the energies are big, but they're not scaling with the central charge as C is big. And so these type of states is what we call light. And they basically said that if the number of states of the CFT here, so they put a restriction here, again, because of modular invariance, because modular invariance relates things that are light to things that are heavy. It related the vacuum state to like the thermal state. So basically by using modular invariance, they showed that if the number of states here was less than an exponential, then you were going to reproduce exactly that phase diagram in the limit that C was going to infinity. So this is a condition. This is what's called a sparseness condition. On light states of the CFT. Not really. So in higher dimensions, you don't have modular invariance. So I think intuitively, I think yes, because this sparseness condition is not quite the same, but it's very, very related, or intuitively, it's very, very related to like the planar limit that is discussed in higher dimensions. So it's like within that same universality class that You want factorizations of like correlation functions, and you want to have what's called a generalized free field description of the CFT, like in the 't Hooft limit of like n equal 4, there's this nice planar limit. This is in the same category because those planar limits in higher dimensional CFTs put conditions on operators whose conformal dimensions are not big. So it's on the first like primaries that you get. So it's not a restriction on black holes in higher dimensions. And so that's why this is also kind of in that same class. But the thing in higher dimensions is that you don't have modular invariance. So what you do at low temperatures or what the light states are doing is not obvious that it should influence the heavy states. But in some sense, I think, like what my gut tells me, but I don't have a proof, but I think once we get better at understanding CFTs in higher dimensions, I think that's going to become more clear. That and it's coming also from the, if you look at the corrections to the black hole entropy, we can see that the corrections are controlled by the light part of the spectrum in any number of dimensions. And so there is a connection there, but it's something that I just have like my gut telling me, but I don't have evidence, but yeah. So formally speaking, no, this is very special to CFT₂, but I think there's something like that there because of this modular invariance.
Can you repeat what is this line doing? What is it representing?
Oh, I'm just basically trying to illustrate what are the type of states that I have in the theory. So you have like different types of states with different numbers of degeneracies. And I'm saying like if you want at high energies to have a density of states that looks like the black hole, then at low energies you cannot exceed this bound. And what's important here is that this, so there's a factor of 2 pi and e. And what's important is that what you need to remember is that the number of light states, so the sparseness condition, the most important lesson, well, besides the fact that it's exponential, is that this bound is independent of C. So that's why it's not an easy bound to impose. It's a very special type of bound. That it's a state that has energy that is not controlled by the central charge. So like a descendant. Yeah, so you're taking basically the central charge to be very big, and you're looking for like states whose energy is not controlled by the central charge. So for instance, a descendant will be light because the energy of a descendant, it's just like an integer, it's not controlled by the central charge that the CFT has, okay? Primaries, that's a little bit, it depends on the type of primaries. There can be primaries that are light, but generically there can also be primaries that are heavy. So there it's a little bit different. But if you want like a lamppost example of what a light state is, descendants are light states. And that's why they're also called like perturbative states. They're like little wiggles. And we also saw that in gravity. They behaved like little wiggles from the gravitational side, okay?
Where are those light states in gravity? Boundary gravitons?
So they can be different things. They can be boundary gravitons are one type of light states, but they can just be like a massive scalar field. Because the mass of the field, it will not be controlled by G Newton. It will be controlled by the AdS radius. So
There wouldn't be another theory without pure gravity?
that's fine, but we're talking about gravity quite generically. So, yeah. So if you have matter in the gravitational theory, basically a light field, a light state is any field whose mass is not controlled by G Newton.
A question on, perhaps it's not very important, but I would have said then that heavy states are the one in which E is of the order of C.
Yeah.
And can you explain, because in the blackboard I see EC bigger than 1.
So the reason why you would put that E is of order C, it comes from here. So when the temperature is of order 1 over 2 pi, remember that the energy, oh, I erased the formula. But this basically, so recall that energy was like C times T squared with some numerical prefactors.
Yes.
So if the temperature is of order 1, then energy is of order C. So black holes already start dominating when the energy is of order C.
No, no, I agree. I just was pointing the thing that you said, that EC bigger than 1 is not the same as E being of order C.
No, well, okay, again, it will depend a little bit on which ensemble you make the conclusions.
Okay, okay.
My biggest problem is that the Cardy formula in the CFT, this is what you have to remember, is that the Cardy formula in the CFT, if you take C to be very large, it's only valid when the energy is much bigger than C.
I think I clarified my confusion. Thank you, thank you.
But in gravity, black holes already start being dominating, like the ensemble, when the energy is of order C. And this is very different from that. Like completely, like, of course, this fits inside there, and that's what I'm illustrating here. So it's kind of like that tail there, but it's there. We still have to explain this whole other part. And so yeah, and so the sparseness condition is something like, okay, if you have a CFT and you think that it will be a good model for black hole physics, the first thing that you have to check, you know that you're going to get the Cardy formula for free, but then the second thing that you check, so this is a more fine-grained condition, you check if you comply with this. If you do not comply with this, goodbye. Your theory is not going to be a good model for black hole physics. Okay. Right, so for instance, if you have so you love AdS₃ times S3 times T4. Is that your favorite theory? Okay, so for example, okay, so let me be then more general. So for example, consider a theory, like, because in string theory, usually these things comes times like a manifold. And this manifold, let me call D the total number of dimensions. So the dimension of the manifold is D minus 3. This, so sorry, let me call this also D light, just to make clear that I'm only talking about the number of states perturbatively. So D light in these cases goes like E to the D minus 1 divided by D. And the reason for that, the way that you can kind of eyeball this computation is that this thing here is basically a box of D dimensions. And then you just do the thermodynamics of like how many states, how many oscillators you can put in a box of D dimensions. So a problem in StatMech, I think you were teaching StatMech, so you can ask your students in the next exam to compute the number of states that you can have in a box of D dimensions. The answer is that the number of states goes at high energies. So for when E is much bigger than 1, it goes like, sorry, let me write this bigger because I'm probably, so it's the exponential of E to the D minus 1 over D. And so even if this box is very big, you can see that this is always less than 1. So at most, when D goes to infinity, it matches what this is called the Hagen-Dorn growth of state. So a QFT on a curved background will never reach the Hagen-Dorn growth of state. So for any like supergravity that you have, which effectively is just quantum field theory on a curved background from the point of view of perturbative physics, so from the point of view of these light states, you're always within this bound. So it's compatible with, yeah, with that. It still allows Hagen-Dorn. So unfortunately, and that's why it's still a non-trivial condition, but it's not stringent enough. So it's kind of funny that theories that have Hagen-Dorn-like growth still admit a Hawking-Page phase transition. So it's again necessary, but not sufficient. So we're just kind of like keep on improving of like, okay, we got Cardy, great. Now this gives us more refined, this touches with this, but then still not enough. Yeah. Okay, so with this, like, I know there's so many, we're basically almost done. With this, I wanted to give you like kind of an idea of like what happens as we're trying to model like quantum gravity through the conformal field theory, and in particularly like trying to answer these questions. Now, I focus here just on the partition function and just on the entropy and trying to match the black hole entropy. But in the in the literature of AdS₃, there's many, many more quantities that you can look at. So just as a final note, so other observables can also be considered in the same fashion, okay? So again, the partition function was just one of them, and I wanted to illustrate here basically how do you organize something as kind of natural as the partition function in a way that it would cater for black hole physics. So how do you see black holes coming out of the CFT? But you can do this, for instance, also for like thermal two-point functions if you're still interested. So thermal correlation functions. It's another observable that you can look at. You can look at entanglement entropy. And people have done this as well. Understand universal properties of entanglement entropy, but then also, if you wanted to get the same physics as black holes, what are constraints such that the entanglement entropy of the CFT matches it? What else? Let's see. Any other thing that you can think about that you compute in AdS₃? Many of you raise your hand and I'm like, oh, I'm working in AdS₃. What is the thing that you compute? Wilson loops, sure. Yeah, but let's put it like expectation values. Yeah, Wilson loops are still okay. They're a little bit boring in 2D, but like, okay, let's put expectation values of operators. So, for instance, in the language of it's not quite Wilson loops, but in the CFTs, there's also a lot of universality in the large C limit on OPE coefficients. So this is also something that is looked at if you go search through the literature, and so forth. And there's also more fancy partition functions. So for instance, here we just did the torus partition function. You can put other Riemann surfaces. So take T2 to a sigma, G, and so forth, okay? So, and in every single one of these observables, basically, something that you're looking for is an answer to that question. How do you organize those observables in the CFT such that gravity is manifest? What are really the conditions such that you match with the classical physics, okay? Ale.
Function we can analyze in many different regimes. It matches the classical gravity there. But is there any way to understand what type of theory of gravity this defines that it's not classical gravity? Is it like something super quantum, something with higher derivatives? Like if I try to define gravity with this CFT₂, it's not going to be this phase transition.
Yeah.
Is it still going to be a theory of gravity?
It depends on who you ask. So back in the day, I grabbed the Ising model. So I was brave and we took C equal to 1/2. And we said, like, basically it was in regards to this question, like, does the Ising model have a way how to understand it gravitationally? And the answer is yes, there's a way. And actually, so this is an old paper, and we showed how it would work when C was less than 1, how you should reorganize observables in the CFT. How should you reorganize the partition function such that it look, for instance, like this Poincare series. So when C is less than 1, you can always reorganize those partition functions such that it looks like the Poincare series, and then it actually makes a very clear connection with the gravitational path integral. This past January, there was a different paper that is also really interesting because it also tells you that there might be different answers to this question. There was a paper in January by Janek, who again grabbed the Ising model, but he wasn't looking at the partition function. He decided to start with the thermal two-point function and trying to see how the thermal two-point function in the Ising model captured quasi-normal modes, like to which extent it would capture the quasi-normal modes of the BT set. Of course, it doesn't have the same decays and plateaus and things, but like there's a regime for which it looks very much like a black hole. And then based on that, he constructed a Chern-Simons theory coupled to matter that was reproducing the same thing. But what's interesting about his proposal, going back to the assumptions that we were saying before, in his version of quantum gravity, he would have said, you don't have to sum over topologies. So his proposal is that you have a fixed topology, but then what gives you modular invariance is the matter fields that you add. So he had like these weird like Wilson line operators in the Chern-Simons thing that gave the modular completion. But then it was doing an excellent job. That funny Chern-Simons theory was giving him the correlation functions of the Ising model at c equal to 1/2. So that's also why it's kind of fun that like even with the assumptions that we had the last lecture, like people are also thinking like, okay, maybe we don't have to sum over topologies. Maybe if you, like how you can restore or match with the CFT physics is via a different way, via different rules. But okay, most of the people like do think that still you have to sum over topologies and stuff. And so then the question is, from the point of view of this partition function, going back to the puzzle that we had in the previous lecture was like, okay, so this is just the thermal part. Then what happens to the rest of the path integral? So what does the CFT partition function tell me as I try to organize it in this fashion? But that's more difficult as a question. But in any case, it's something that people are thinking about, trying to work on. So okay, so I think, yeah, lunchtime, we're hungry. So I'm going to finish here and then you'll ask some questions. So thank you for your attention.
Okay, thanks Ale for the course. More questions?
Excuse me, I don't know if I understand correctly, but we want the CFT to match the behavior of gravity, right? So if C is too big, then we are not in. We want like C to be in between of the two conditions you did in yellow.
Look,
I am just
C
trying
being
to.
very big means that you're reaching the semi-classical limit of gravity.
Okay.
So
but
C very big means that G Newton is going to 0.
Okay.
So therefore you trust classical gravity.
Okay.
Period. Done. End of sentence.
Okay, but in the side of the CFT, you cannot have the energy be of the order of C?
No,
That's
you
what-
can.
yeah? Okay. But
This is just a statement of the validity of the Cardy formula.
yes, but
The Cardy formula is something very specific, and I'm just saying when does that expression, when is that equation a good approximation for the CFT?
okay. But that will be conditions over the CFT or over gravity?
It's a condition over this formula.
Okay.
It's when do I trust this formula? So this was making a prediction. It was telling me that the number of states was going like this. So it's like, when is this a good approximation?
Okay. So
The CFT has some density of states given by whoever gave you the CFT. And it's a question of like, when is this well approximated by this?
okay.
And that's what gives me this box.
Thank you. I have another question.
I think there was a question in the back, so.
Yeah, so this is in regards with your, again, it's a little tangential, but you said you worked with the Ising model with C-half. So could this also work with, let's say, negative C's and maybe like non-unitary, so it's unitarity?
I think, yeah, I know if the paper hasn't come, my head this year has been a bit fuzzy, but I know that a group at the other ICTP in Trieste, kind of funnily, so Agnese Bissi and some of postdocs in Trieste, they were working on like versions of this for non-unitary CFTs.
Non-unitary CFTs.
And seeing if they can like, although there you will have some peculiarities and you might get a little bit nervous about like non-unitary CFTs, but there are many like, although they're non-unitary, there's some very nice models that are
Right.
non-unitary in 2 dimensions,
Yes.
and they're trying to see if in those models you can get closer to gravitational features just to have an understanding of like these pathologies that we saw last lecture. So I know that they're working on it. I think the paper has not come out, but you should keep an eye, or if you run into Agnese, yeah, she was telling me about that, the fact that she's working on that. So also, it's a good question. So then if the paper comes out, you can see what they did and if they cover the right models.
Anyone else?
I have a question, but you can disregard it. Now, we'll discuss.
Well, you already have the microphone, so.
No, but okay, if there's nothing else, we're, oh no, over there. You figured out the temperature? No, okay. Sorry, I didn't, I'm sorry. I'll
I
shut up.
wanted to ask you your intuition on this discussion on, we are averaging the gravity side and fixing the CFT side, but maybe
We're averaging the gravity side. What do you mean?
you are computing a partition function, summing over all solutions and topologies that are compatible.
There's no averaging.
Well,
It's a
you
sum.
can, okay, it's a sum. But maybe I wanted to ask your intuition on maybe averaging or maybe doing a sum on in the CFT side and fixing the topology and the geometry and the gravity side.
That's not going to help you. So the reason why people have been thinking in terms of averaging is because of like this type of universality. Okay, there's other reasons that come from lower dimensional gravity, but let me just try to answer your question in the universe of like 2D CFTs. And the thing that happens in 2D CFTs is that a lot of things can be constrained by modular invariance. There's many regimes of parameter space that are basically controlled by symmetry. Not everything. So when you get to the details, of course, you need to know which theory you have. But there's a whole, that's also why the observables that I was picking there, there's many of them which you can say quite a lot about them just based on symmetries. And so that makes you like think that like you can think in terms of like buckets of theories, like kind of ensembles of theories, of like saying like, it's just like some collective of them are doing this, and maybe if you average over them, so in a particular way, that collective becomes the exact gravity answer. So that's one line of thought. And it comes because of all of this universality of things that many things are just dictated by modular invariance and conformal symmetry and Virasoro symmetry. I'm not a huge fan of that point of view. But okay, since we still haven't figured out what quantum gravity is, I am also open-minded if people want to think along those ways. But I feel it gives me less control because, yeah, in any case. But that's what's happening with that picture, that you think that what gravity is computing for you is just an appropriate average on the CFT. Now, other people say, no. There is an average, but it's not among different types of theories. It's just a sector of the theory that is behaving in this kind of like coarse way. So that's another line of thought that I think it's a bit more constructive on like trying to understand that CFTs that have large central charges have universal sectors, and we need to have better ways how to describe those universal sectors. The issue is that if you open the big yellow book and you try to look for a theory that complies with these two criteria, I can tell you right away that book doesn't have, like, first of all, forget about the second one. You might have thought, oh, that's pretty tough. The book does a great job at characterizing theories with C less than 1. The only theory that will have C bigger than 1 is like a free boson, like n free bosons, where you take the number of bosons to be large. We are terrible at characterizing and solving conformal field theories when the central charge is bigger than 1. And so the issue right now, the tension in trying to answer these questions, is that we're extremely ignorant about the space of conformal field theories when the central charge is bigger than 1. We know properties, we know symmetries, we know this is how you should describe them. But if you tell me like, oh, write for me a Lagrangian, give me some set of like a list of primary operators and stuff, like, yeah, we're pretty bad at that.
The approach you were following up to last class didn't work.
The
approach up to last class didn't work. We couldn't have the trace like you wanted.
Yeah.
But we still use the same C. Shouldn't have a correction to the C. Why we use still
sorry,
the
which
same
part
C?
should have a correction? Sorry, like the...
C equal to 3L.
Yeah, but all of this, because I'm taking C to be very large, you won't see the corrections at this level.
But it depends on parameters which controls what we want to
Yeah. So
compare.
as you get more fine grain, you will care a bit more how those corrections go about. But at this, to first order, you're just taking C to be very big. But indeed, like if once you have a candidate of like, this will do the trick, and I will know what the CFT is, and then I will want to interpret it in terms of the gravitational path integral and solve the problems of the previous lecture, then yes, then you will want to know everything that is going on. You will want to know what primaries are involved. You want to know exactly how things are getting matched. But right now, I'm talking about things that are all, if you want, in the strict C going to infinity limit. And so I'm not seeing the corrections at this level of this course because we're just doing the semi-classical computation.
Thank you.
Okay, let me close by thanking Ale for the beautiful course, and also because she's